I'm Takamizawa from Yokohama, very close to here. And maybe you will be happy because I'm not good at English. Very bad. But study itself is good. So, and also my talk would encourage you, Japanese people, because I am still very domestic person, very and not international, not global. So that's my finding. It's now this MF 2016 organizing committee. Many thanks to organizing committee give me a chance to talk for you. And so I'm very grateful. It's very grateful to me. And so especially thanks to Kuroda sensei for picking me up to here with the same time, sharing the same time with you. So my talk title is Metal Mimicking Organic Compounds in Shape Restoration. So metal mimicking makes you feel my study is just tracing another study already established in another field. But it is not true. I bravely intend to find deep or fundamental finding. I intended to grasp or find the new discovery. So, okay, I forgot something. So next slide. So over here, you can see the beautiful shape recovery, shape restoration cycle of a single crystal. So this crystal is an organic crystal composing of this very simple simple organic compound, terephthalamide. So by applying the force on this and this direction, so that manner is shear. So this is a shear induces new crystal domain. And this new crystal domain has another crystal structure in this case. So this is shear induced phase transition. And in this crystal, terephthalamide gather to form intermolecular hydrogen bonding network solid. And by analysis, you can find a very strict correlation in molecular orientation, change in molecular orientation, fitting of crystal cell, and the shape of crystal deformation crystal. So, in fact, when I found this very strange behavior in my laboratory, I was very glad, but very happy. But after that, I was very disappointed. So by knowing the fact that such physical property was already known in a very, very specific kind of metal alloys. And you may know this physical property is called superelasticity. In superelastic metal alloys, or shape memory alloys. So this, in this case, so shape restoring manner is physically the same as known in shape memory alloys in principle. So I was very disappointed. And so first I have to teach you. You should learn the superelasticity. So before entering I explaining the insignificance of my findings. Okay. So any kind of materials, by applying the force, every kind of materials should deform. And deformation is categorized into elastic deformation and plastic deformation. The elastic deformation is consisting of energy elasticity and very famous lava elasticity. And this is very strange. But you know the energetic elasticity. This is, of course, shape is restored, recovery, automatically. And in plastic deformation, so usually we say plasticity or plastic deformation. That means very, very complicated plasticity. That means plasticity itself includes many different kind of events at once. So, but we introduce some kind of very easily understandable deformation, such as slip deformation or diffusionless, non-diffusion deformation process. That is, of course, a little bit rare than others. After multi-synthetic transformation occurs, a very specific kind of alloys can recover in its shape. So that is called superelasticity. So you should know so superelasticity is not elasticity, but rather plasticity. So, so the superelastic alloys are very applicable. And I listed some famous application here. And, but the number of superelastic alloys or shape memory alloys, so material kind, number is very limited, around 20 as present. And titanium nickel alloy, it is, some people say, titanium nickel is God's alloy, or alloy of gods. So because the titanium nickel is only one presentative alloys, shape memory superelastic alloys. So very limited in kind in alloys. So if materials deforming, sequentially deforming process proceeds. So from elasticity and passing the limitation of elastic deformation, plasticity take over, and finally materials break down. So this shows a elastic process. And after passing the yield point, plastic deformation occurs and leaves permanent residual strain after removing the force. So this is titanium nickel chip memory alloys. So now the same plastic deformation occurs. And warmed this material up to the more than the transition temperature. So the higher temperature region, this material has a superelastic phase, crystal phase capable of superelasticity. And in superelastic region, plastic deformation, the range is very wide. And surprisingly, very strangely, spontaneously regain recovery with constant force. So this long-range deformation ability and constant force, recovery force. So these are very unique and very important properties for shape recovery, superelastic alloys. So you can see some stents in blood cell, and maybe some of you may be treated when seeing a doctor. So teeth brace. So long and continuously keeping the same power. So very useful. So maybe you can understand what I want to say about my findings. So because my finding is organic materials. So previous materials are only metallic materials and very small kind of materials, number of materials. So maybe organic materials can expand, okay? So the importance of my findings can be understood more by hitting the history of superelasticity. So we have to date back to about 100 years ago. It is said, first observation of superelasticity, first description of the superelasticity is believed in this paper. So 1932 paper. So author reported the elastic-like behavior in gold cadmium alloy during the study on electric conductivity. Okay, very accidentally found. And it is also said that about 20 years later from here, shape memory effect, the property of shape memory effect was written in this paper, they say. So this is the same alloy, same kind of alloy. And then titanium nickel alloy. So this is very useful alloy. And the finding of superelasticity and shape memory effect in titanium nickel alloy is very interesting. So nickel alloy. So titanium nickel alloy was developed for shock absorbing materials to submarine in US Navy. Okay. So now I can say the science of superelasticity started in 1932. And in 1960s, so-called shape memory alloys occurred. But they could not replace superelastic alloys because of completely difference in physical mechanisms. Okay? Oh, okay. あれちょっとずれたかな。Sorry. And now we are here. So new superelastic materials and new shape memory crystal. Here is I talk later. And this is organic solid. So organic solid is very easy materials for chemists. Okay, so I expect this finding allow rapid and extensive development of this discipline. Okay, so to generate a new material science related to superelasticity. And in shape memory effect in alloys is very unique. So by heating the alloys, so recovery force go up, so strengthening, okay, very mighty. So that is, of course, very useful properties. So here you can compare shape memory alloys and shape memory polymer here. So shape memory alloys, by heating, getting tends to be hard, tends to hard, and very quick shape recovery motion. And in polymer, heating makes materials soft, and the recovery motion is very feeble. So this is the reason why shape memory polymers are so many number of polymers, zero, but cannot replace the metal alloys in this field. So shape memory alloys are applied for thermal actuating device, such as guide wire or thermal heating drive valves. Okay. So I found shape memory effect in organic crystal. So here are now the deformation and heat sweeping. So this crystal made of stable ionic species, so cation, organic cation and organic anion. And this is, I intended to introduce the thermal transition behavior in the organosuperelastic crystal. So you can see the completely regains the shape as if nothing had happened. Okay? So this is a very exact example, measurement, results of measurements, and low temperature phase, because this has transition temperature transition temperature, critical temperature at 123 centigrades. So below that point, only Martenstick transformation without superelastic behavior. And after passing the transition point, another crystal phase occur. And this crystal phase can express superelasticity. So in this graph, the force increases along with temperature rise. Okay, so that is very really the same shape memory effect in metal alloys. Okay. So now here you can see this red line is my crystal. So qualitatively similar to SMA and completely opposite to SMP. Okay. So now I can say the organic crystal can reproduce not only superelasticity, but also shape memory effect. Okay. Okay. So now I have to comment on the size of crystal. So can you find a crystal that is a typical size crystal for our experiment? Maybe no. So very tiny, very small. So that is very difficult to visual experiments because such small size is too small in common sense of the people who handling the elastic materials. Okay? So fortunately, this this compound can easily grow into big size crystal because ionic crystal. So with the help of proper organic solvent. Okay. So then I prepared a big crystal and cleaved it into this size crystal specimen. And using the visual, very practical experiment. So this crystal is 0.6 gram in self-weight, but easily lifting up 100 gram weights, and sequentially lifting up along with the temperature rise. That means elevating the temperature, along with the elevating temperature, mighty. So strength. Okay. So the most important point of my finding is I introduced superelasticity in chemistry. Okay? And if I have to say that this simply, the atoms in alloys are replaced with molecules. Okay? So from the property of nature of molecules can produce superelasticity, various kind of superelasticity possibility. Okay, and furthermore, so organic system can be regulated by the power of chemistry. So synthetic chemistry, supermolecular chemistry, or crystal engineering, and now progressing functional material chemistry. So the very new or multifunctionalization of materials. This organosuperelastic chemistry may lead us to new world, maybe. Okay. So today, I just tell about the 2 of 4, but so these 4 solids make me think almost cover the space of materials world. So that means so now 4, but solid types. So ionic, van der Waals, hydrogen bond, and material kinds, organic compounds, and metal complex. And this metal complex is porous and coordination polymer. So that means the polymer and the porous. The porous will be very important in the future for saving the material's weight. And so multiplicity of component. So I think all materials might be superelastic materials, but it is I can't understand. I can't know. I don't know it is true or not. So our findings organic crystal, organic solid. So I think this region is more general than alloys. So I think the progress of this area, molecules and atoms unified united to form new material science with respect to superelasticity. And I want to say my findings, discovery. So that's, as I told you, so superelasticity itself was already known in metal alloys. So the metal compound itself is used in elastic for uses. So this line is continuously connected. But in organic solid, they are most poor solid for elastic use. So this line is not connected in concept. So very strange, we feel. And the superelastic index jump in this side. Superelastic index is the indicator how easy to use superelasticity. So the lower lower force requirement, required force, lower required force to enter superelastic transformation, and relatively high energy storage efficiency. Now I want to compare with superconductivity, in the case of superconductivity. So metal oxide is insulated, so this is not connected directly like this. And so that if this high temperature superconductor can be called discovery, I can say my finding is discovery, a fundamental discovery. Because here, metal oxide is still inorganic materials. But here, we can ask organic solids already. So, and elasticity and plasticity is fundamental properties, physical properties for all kind of metal. Any kind of metal should have these properties. So the very fundamental properties and very good controllability using the chemical power in this region is expected. So I want to say that organosuperelastic research is not only for the replacing shape memory alloys or superelastic alloys, but that is go forward in the very various kind of direction and dimensions in future. Okay. So now I'm very poor at English, but I opened like you. I'm very like you, okay? Very similar. But I opened the new world, opened a new door to the new material science in terms of superelasticity. Okay? Okay. My talk, can I finish my talk? Okay. Okay. So thank you for your kind attention.
Okay, students who want to ask questions, line up.
So in advance, I look up for information on your research and and then I found that you also research on metals which would absorb hydrogen gas, and but you find these superelastic organo compounds. So what was the hint for you to find such superelasticity in different fields?
So this is very important question. Maybe knowing for myself. So I thought intended to find a new physical element in the material science.
Yep.
So I raise here conductivity, dielectricity, magnetism. That is very usual, very famous, and I think this is very important for material science. And I found that this is related to electron, and maybe here, nucleon or quark, related to the nucleon quark, such a physical property might be here.
Yeah.
But it will be very difficult to use at will. So of course, I was longing for very sophisticated physical materials. I wanted to seek for, but this direction and here, I think very difficult to find for me. So the opposite direction, so only mere aggregation related to the aggregation, elasticity and plasticity already settled in here. So I was wondering, something is in here, okay? So this is intrinsically, completely different from electron, okay? So only aggregates. So if I find this, that will be very general. And all materials should have such properties. So, but it is very contradictory for me. So if such property is existing, why nobody had not seen? So because I'm very normal person like you, so if such property existed here, I can observe not far from here, in front of me. So so the fact nobody has observed such property. So I think the most poorest materials that has not been not so many times treated by the many people. So I selected the organic single crystal. That is poorest material for elasticity. So I decided to start such exploring experiment to find a new element, physical element, by crystalline all regions in my laboratory.
Yeah.
Yeah.
I got it.
I find it. Okay.
Thank you very much.
I have a question. When you push telephoto amide, there seems a shadow area. What's that? TPA.
Actually, that is clear and no color. But we have to make contrast by polarizer. Can you understand? Yeah, image. But because it's a clear crystal, very difficult to find the boundary. Okay?
Okay, thank you.
I'm sorry. I didn't talk about that.
My question may be similar to what the first boy mentioned, but when my question is more of how it is that you came to the organic compound, because there has long been that metallic compound that has super elastic properties, and then now you've sort of found it in the organic compounds, and then you mentioned that they were poor. Could you elaborate? I didn't know what you meant by poor. The poor as in
So poor is for what? What for?
in finding that. Yeah.
This right?
Yeah.
So that if the elasticity and plasticity is all material kind has such properties. So the many people, many enormous people, usually touching and using the materials around us.
Yeah.
So, but if here exists, if something exists in here, one point is maybe very boring material. So I think the organic solid or table salt maybe poor. So
okay.
I selected that, and maybe I think that if such physical property exists, the sign of such property might be very feeble. So I have to use a single crystal. So if the crystal structure causes such unknown physical property, I can detect by the enhancing. Can you understand?
Oh, okay.
Okay.
Yeah, I
Okay.
got it. Yeah, thank you.
Thank you for preparing a wonderful lecture for us. I have a simple question. You introduced for us about four type of Superelastic original crystal on this lecture. So I want to ask you how many kinds superelastic original crystal which have already have been discovered are.
So now we found more and more in my laboratory.
Oh,
But now I can, my laboratory has more than a dozen of crystals, material, different compounds of crystals.
Yes.
And it is very interesting. Now 2 years almost, 2 years already passed
yes.
after my report. But now, no reports in other country, only me. Okay.
Okay, thank you very much.
Thank you for interesting of iron's material. I have a question. It is, how do you do study of materials? Is it a repeat of try and error?
Yeah, of course, so real finding, real discovery is such thing. So because I don't know how to find, how to detect the property, of course. So try and error means so the organic materials and materials, the number of materials, kind of materials is number is very huge. So it is impossible for me to do everything, okay, every kind. So this is a important thought, or of course brave heart, because there is a possibility such a property is not existing. Okay, so I think the heart and thought. Okay, because maybe the. So I'm almost alone. So. So I have only 2 hands, okay, and 1 head, 1 brain. So I have to choice only one thing. But only one thing I chose. After I chose, I have to be devoted to do. Okay.
Okay, thank you.
May I explain something? I can explain superelasticity. Okay. So you have, all of you know what elasticity is. And in your system, I think you are very close to equilibrium. You distort the structure slightly. The atoms are not moving much. And then they easily go back. I think your hydrogen bonded system, you go far away from equilibrium. So you get a rotation like this of the molecules. And then it's a big thing to come back. I enjoyed your talk, but the discoverer was Arne Ölander, a friend of mine. 1932, he published in metals, and you discovered it in organic solvents. So it's a very important, very interesting area. Thank you.
Thank you very much. You need?
Yes. So you talked about how, with the shape memory effect, how heating it can return it to the original shape. But how is that memorized? How is that shape memorized in the first place on an atomic level?
So the shape memory effect is meaning the temperature dependency of shape recovery, and the shape memory means memorize. So in order to do memorize, that is once time melting needs a melting. So in shape memory alloys and the shape memory polymer, that is like melting. It is difficult to explain about the case in alloys, but the alloys is very difficult. I think my English ability cannot do work well. But so in polymer system, so the crystalline domains melting,
Yep.
and crystallize. So that is the initial shape for the second shape memory effect. Okay.
Thank you.
Can you understand? My English bad. Okay.
Okay. And this conclude the speaker program. Next is the panel discussions. Thank you for the speaker.